Hey, I'd like to do a couple more curve sketching examples just so that you get a little bit of extra practice with a little bit of help. So here we go. Jumping right in, let's take a look at the function f of x equals x squared e to the 3x defined for all real numbers, so its domain all real numbers. And we can start our picture with a graph like this since we're going to need both positive and negative values of x. Let's start by finding the x and y intercepts. The y-intercept is very easy. Plug in x equals 0, and you get that the function value is 0. And so there's a y-intercept that is also an x-intercept at the origin. Let's see if there are any other x-intercepts. We'll take this function, set it equal to 0, and solve. And when we do that, we get that either x squared is 0, in which case x is 0, or e to the 3x is equal to 0, which never happens. E to any power is always positive. And so the only x-intercept is the point that's also the y-intercept, 0, 0. All right, let's go ahead and look for critical points. To do that, we take the derivative, set it equal to 0, and solve. And to take the derivative, you need the product rule. You have to be a little careful with the derivative of e to the 3x. You need the chain rule there, and you get this expression here. And when you set it equal to 0, to solve this, you want to try to factor that expression so that instead of getting something plus something equals 0, we have something times something equals 0. That's much more useful. And you factor it by taking out the largest common factor in each term, and the largest common factor is x times e to the 3x. So you get this expression here, x times e to the 3x times 2 plus 3x. And x equals 0 when x equals 0. That's no surprise. When does e to the 3x equal 0? Well, still never. E to the 3x is never 0. And then 2 plus 3x is equal to 0 when x is equal to negative 2/3. And so we have two critical points, one at x equals 0 and one at x equals negative 2/3. We'd like to know if those critical points are relative maxima or minima. This problem does not scream second derivative test to me. I mean, the first derivative is complicated enough with two terms, each of which is a product. If we took the second derivative, we would need the product rule twice, and we'd have some horrible mess. And so I would say that for this problem, probably easier to use the first derivative test. And so we set up our chart of x values and values of the derivative. We put in our critical points at negative 2/3 and 0. The derivative is 0 at both of those points. And then we need a point to the left of negative 2/3, a point between negative 2/3 and 0, and a point to the right of 0. And so I'll pick points that I think will make the arithmetic easy. And I'll use the factored form of the derivative that I have right here and used to find the critical points to evaluate the derivative at these other points, negative 1, negative 1/3, and 1. And when you do, so first of all, notice that e to the 3x is always positive, and you plug in these values, and you get that the function is, the derivative is positive at negative 1, so the function is increasing there. The derivative is negative at negative 1/3, so the function is decreasing there. And the derivative is positive at 1, and so the function is increasing there. And so by the first derivative test, we know we have a relative maximum at x equals negative 2/3 and a relative minimum at x equals 0. We're still not ready to put these points on the graph. I guess we've already put the point x equals 0 on the graph, but we don't know where to put the point where x equals negative 2/3 is on the graph until we figure out the y value when x is negative 2/3. And when you evaluate the function at negative 2/3, do a little bit of work, and you end up with 4 over 9e squared. And so the relative maximum is at negative 2/3, 4 over 9e squared. And for the sake of sketching this, you ask yourself, what kind of number is 4 over 9e squared? Well, e is some number between 2 and 3, a little bit closer to 3, and that makes e squared somewhere between 4 and 9, a little closer to 9, which makes 9e squared, somewhere between 36 and 81, and more on the larger side there. And so what's 4 over some number between 36 and 81? Well, it's a small fraction, is really what it comes down to. But for the sake of the picture, I'm going to change the scale on the y-axis to be larger than the scale on the x-axis so that I can sort of exaggerate the features of this graph. And here I've plotted the point negative 2/3, 4 over 9e squared on our graph. So far we have a graph with 2 points on it. And we know that this point here at negative 2/3, 4 over 9e squared is a relative maximum, and the point at 0, 0 is a relative minimum. And that tells us a little something. It means that we can see that the graph is going to do a little bit like what I just sketched in right there. And we could go a little bit further and connect those two pieces there. Nothing especially interesting happens between them. There's certainly no critical points. There certainly is an inflection point in between them because it's concave down at negative 2/3 and concave up at 0. And so we could conceivably find that point, but we have some picture of what happens in this like very small area close to the center of the graph. And I've made us some room for our next calculations. All we're really missing here is what happens as the x values get larger and what happens as the x values get smaller. This is a question of limits. We need to find the limit as x approaches infinity of this function and the limit as x approaches negative infinity of this function. Let's first consider the limit as x approaches infinity. Well, as x approaches infinity, x squared certainly approaches infinity, and e to the 3x certainly approaches infinity. And so this is of the form infinity times infinity, and there's no doubt about it, that's equal to infinity. Which lets us complete the right-hand side of our picture. As the x values get larger, this function is going off to infinity. And we now have to consider the limit as x approaches negative infinity of x squared times e to the 3x. Well, as x approaches negative infinity, x squared is approaching infinity, but e to the 3x is approaching 0. You put in a large negative number like negative 1 trillion. What's e to the negative 3 trillion? It's 1 over e to the 3 trillion. That's a very small number, and so this is of the form 0 times infinity. And that is an indeterminate form, and the trick when you have something in that indeterminate form is to rewrite it either in the form infinity over infinity or in the form 0 over 0. And in this case, that's very easy to do. Multiplying by e to the 3x, the same thing as dividing by e to the negative 3x, because e to the negative 3x is 1 over e to the 3x. And if you write it like this, then this is of the form infinity over infinity. And just to make sure we understand why, probably you can see why the numerator is going to infinity, but take a very large negative number like negative 1 trillion, and what do you get when you plug it into e to the negative 3x? You get e to the negative 3 times negative 1 trillion, which is e to the positive 3 trillion, which is a giant number. And that's why the denominator also going to infinity. So since we have something of the form infinity over infinity, we can use L'Hopital's rule and get that this is the limit as x approaches negative infinity of the derivative of the numerator divided by the derivative of the denominator. This is still of the form infinity over infinity, and so we can use L'Hopital's rule again. And we get the limit as x approaches negative infinity of 2 over 9e to the negative 3x. This is no longer of the form infinity over infinity. It's of the form 2 over infinity because the denominator is still going to infinity. And so this limit is equal to 0. And since the function is going to 0 as x goes to negative infinity, that lets us finish our graph. We have a picture that shows, the function going to 0 now as x goes to negative infinity. There are some interesting things happening with the concavity. This function is concave up in here and concave down in there and concave up again in here and all the way on forever. And so there's an inflection point somewhere over here and another inflection point somewhere over here. And if we really wanted to, we could find the precise x values and y values of those inflection points, but good enough. We have a decent sketch of the picture. We can just call it done. Okay, I just want to do one more. This function, f of x equals x squared minus 3 over x cubed, defined for all real numbers except 0, because you're not allowed to divide by 0. And since it's not defined at 0, it can't possibly have a y-intercept, but we can find the x-intercepts by setting this function equal to 0 and solving. And we get that there are x-intercepts at the positive and negative square root of 3. And so I've sketched them in right there. If you really wanted to know where they were in terms of 1s and 2s and this, etc., square root of 3, some number bigger than 1 and smaller than 2. But before we go much further, I'd like to investigate, there's some sort of symmetry happening there that is actually going to be quite useful for us. Look what happens if you evaluate the function at negative x. Well, after a little bit of work, you find that f of negative x is the negative of the original function, or negative f of x. This is what we call an odd function. And so it has symmetry, we call it symmetry about the origin, meaning if you drew the picture on one side of the graph, you could rotate it around the origin by 180 degrees and get the picture on the other side of the graph. And so all we really have to do is graph this function to the right of the y-axis, and that will tell us what the graph of the function looks like to the left of the y-axis. And we might save a little bit of work. Let me give you an example of what I mean. This function is not defined at x equals 0, and yet is defined for all other real numbers. So one thing we're going to have to consider is what is the limit as x approaches 0, both from the right and from the left of this function? Well, because it has odd symmetry, we only have to consider one of those things. So let's look at the limit as x approaches 0 from the right. As x approaches 0 from the right, well, the denominator is approaching 0, the numerator is approaching negative 3, and so we expect this to go to infinity or negative infinity. And so this is one of those examples, one of those situations where we want to pick some value close to 0 from the right, do a calculation, and determine what happens. For example, here I've picked x equal to 1/100th, a small number to the right of 0. And I've plugged it into the expression x squared minus 3 over x cubed. I get 1/100th squared minus 3 over 1/100th cubed. In the numerator, I get some number that's very close to negative 3. It's not quite negative 3, it's slightly smaller, but 1/100th squared minus negative 3, just about negative 3. In the denominator, I get 1/100th cubed, which is 1/1,000,000th, and so this number is precisely equal to 3 million. And so that lets me know that this limit is equal to negative infinity. And so I've drawn that in on the graph right here. We could probably deduce the limit as x approaches 0 from the left right now, but instead we'll try to use symmetry, and so we'll just concentrate on the picture to the right. Let's move on and find the critical points and determine if they're relative extrema. To take the derivative, you need the quotient rule. You set that equal to 0, you do a little simplifying, and then you solve, and then you get that x is equal to 0, x is equal to 3, or x is equal to negative 3. But in fact, x is certainly not equal to 0 because the function is not defined at x equals 0, and so the only critical points are at 3 and negative 3. I'm only going to focus at the critical point at 3, since I'm going to try to draw the picture on the right-hand side of the graph and then deduce what the picture on the left-hand side looks like. And so I need points to the left and right of 3 to test in the derivative, and I want points that are going to make the calculation easy, and I have to stay away from 0. So when I say to the left of 3, I mean to the left of 3 and the right of 0. That's why I picked 1, and I picked 100 to the right of 3 just so that it would hopefully make it obvious whether the derivative is positive or negative. From this expression right here, we get that the derivative is this expression right here, 9x squared minus x to the 4th over x to the 6th. And it's easy to see that f prime of 1 is a positive number, and so the function is increasing to the left of 3. And hopefully it's also easy to see that f prime of 100 is a negative number. 9 times 100 squared might be large, but 100 to the 4th is certainly much larger, and so we have a negative number in the numerator there, and 100 to the 6th is a positive number, and so this is negative, and the function is decreasing to the right of 3. And that tells us that the function has a relative maximum at x equals 3. We need to know the y value when x equals 3, so we plug that into the function. And after doing a little bit of arithmetic, we get the value 2/9. So the relative maximum is at 3/2. So now I can add to my graph. It passes through the x-axis at the x-intercept at the square root of 3, and then has a relative maximum at 3/2. All that's left is to determine the end behavior, what happens as x gets large, meaning what is the limit as x approaches infinity. And you can do this either by L'Hopital's rule, since it's of the form infinity over infinity, or by algebra and the limit laws. You could divide the numerator and denominator by x cubed, and then use the limit laws to compute that this limit is equal to 0. And that gives us the rest of the picture on the right-hand side of the graph. It looks something like that, aside from my sort of jiggly line right there. And now if we wanted to draw the picture on the left-hand side of the graph, imagine rotating that picture around the origin. In other words, imagining that it's rigid, fix it to the origin and spin it by 180 degrees and see what you get. And you get something that looks sort of like that. Did a little cleaning up so that we could see our graph better, but more or less, this is what our function looks like. And if you didn't want to use the symmetry, if that made you uncomfortable, no problem. You would just do the same things that we did to the right of the graph to the left of the graph. But you'd have to consider, is the point at -3, which I haven't drawn in and probably should have, right here. You'd have to consider the critical point at -3 and determine that it was a minimum. You'd have to look at the limit as x approaches 0 from the left and see that it's infinity. And you'd have to look at the limit as x approaches -infinity and see that that's equal to 0. And then you get basically the picture that we have here. Okay, I hope those couple of extra examples on curve sketching were helpful. As I mentioned in my last video, we'll practice some of these in class. Look forward to seeing you then.